the back propagation in neural network. How do we do the back propagation? What is back propagation? We'll take a look at it. In the case of neural network, so far we learned about what is forward propagation. Now we will take a look at the back propagation. It is the essence of neural network training. By doing the back propagation, we are going to fine tune the weights of the neural net based on the error rate obtained in the epoch. Epoch is nothing but your iteration. Okay, so in the case of back propagation in neural network, the gradient descent algorithm is used. Don't forget it. Okay, this is we can say this algorithm is probably the most fundamental building block in a neural network. The idea of this back propagation is to minimize the cost by adjusting network speeds. For example, this is your neural network. Okay, in this case, this is your forward propagation. So in this case, what the idea of back propagation, so what happens is it picks up the error and then it passes the error back. See, your input layer passes the values to your hidden layer. Hidden layer's output will be passed as an input to your output layer. Even the output layer, it does the same thing. Z equal to this value into this one, and then it applies the activation function, and then only it gives us the final predicted probability. Okay, and once you get the predicted probability, in this case is the predicted probability is the actual value, you get some error. So in this case, in output layer we have two neurons. One is for class 1, other one is class 0. So what is the probability for class 1? What is the probability for class 2? When you add these two, right? Sorry, when you find out the error for these two, right? You will get the total error. So in the case of back propagation, what happens once the forward propagation is done? The idea of this one is to minimize the cost function, right? It tries to minimize the cost function, the error, by passing the error back, in terms of adjusting the weights of the previous layers. Okay, the level. So now by adjusting the value of the previous layer, right? But what happens in this case, iteratively it adjusts the values of the previous layers, and then it will try to reduce the error to the super minimum. Okay, it keep iterates as long as the it keep iterates by changing the values of the weights, and it will try to reduce the error to super minimum. So that is the whole objective of the back propagation. We want to find out the minimum value for the cost function, right? So now we will take a look at how exactly this one works. And here I have used some sample values for weights. Okay, and with this weights, we will take a look at um, we will use the chain rule. With the chain rule, we will try to write we will write them the differentiation function. Okay, using the chain rule, and then we will see how we can reduce the error by doing the back propagation, right? So in this case also, the loss function is going to be your gradient descent algorithm. And you remember, in the case of gradient descent, two important aspect. One is you need to remember the two aspect. The one is the gradient. You need to find out the gradient, and once the gradient is obtained, and and it has to know the step size, right? So the learning rate, you need to use it for the step size, and with the help of the learning rate, and by taking the product on the learning rate and the gradient, and if you subtract that value from the current weight, you will get the new weight. That is the whole idea of using this one. Before we jump in here, what I would suggest, right, we will take a look at chain rule, because you need to be familiar with the chain rule before we proceed with the writing the derivative for the gradient descent or back propagation. Okay, we have something called chain rule. You should be knowing about this chain rule before we proceed with that. The chain rule tells us how to find the derivative of a composite function. Okay, which means one function is nested over the other. And the second point is you need to understand, identify the inner function and the outer function. See, this works something like this. In the case of, for example, I want to find out dou y by dou x, okay, which is nothing but find a derivative. I want to find out the derivative. For example, I have something called y is equivalent to 2x plus 1 to the power 6. This is the value I have it. And if I take the derivative dou y by dou x of this one, and how it works is the chain rule, the derivative of the outside function. You need to take the derivative of the outside function first, and then you need to multiply that outside function derivative value with the derivative of your inside function. I'll just write it here: derivative of outside function okay into the derivative of inside function. Okay, in this case, what is the derivative of this? First, we need to take the derivative of outside function, and then with that value, you need to take a product with the derivative or inside function's value. So in this case, what is the derivative of your outside function? In this case, the outside function is 6 here. Here you have 6 here. In this case, right, what we need to do is to take the derivative to outside function. You need to know the power rule. We discussed about power rule, right? This one will come in front of this one. 6 into 2x plus 1 and 6 minus 1. The 2x plus 1 raised to the power 6 minus 1. This one will give you 5. 2x plus 1 to the power 5. Here you have 6 here. And then if you take the partial derivative on this one, what will happen? The partial derivative in this case, y is with respect to x is this one, right? The partial derivative, since we are taking the partial derivative with respect to x, and the rest of the will be considered as 0. So this one will become 0 and this one will go away. And you are left with only the 2x here, okay? And sorry, the coefficient of x is 2, right, here. And here what will happen is 6 into 2x plus 1 into 2. The coefficient of your x is 2 here because we are taking the partial derivative with respect to x. This one will go away. Okay, 6 into 2x plus 2 will be there. Okay, so in this case, what will happen is, 12, right? So 12 into 2x, we can say like that, okay? But here 2x plus 1 will be there because we are not going to do anything inside of the function. We are going to leave it as it is. So 2 into 6, 12 into 2x plus 1. Okay, next one is we are, here what happened? We just took the derivative of your outside function. In this case, the power rule comes into picture. The 6 has to come in front. And okay, we did the outer thing, sorry, 6 here. And then the inner function, you need to take the derivative inside function. The derivative inside function, when you take the partial with respect to x, here what happens is 2 will, the 2 will come outside. This 2, because the coefficient of the x is 2 here, and 2 will come here. 6 into 2, 12 plus 2x plus 1 will come here, but we are taking the partial here. Ideally 12 into 2x will come here. So this is what you are this is how you need to use the chain rule, using which we can find out the derivative. So here the steps: the function must be a composite function for which which means one function is nested over the other. Look here, this function is nested over the other outside function, and we need to find out the derivative of outer function, leaving the inner function as it is, and then find the derivative. Once you found the derivative of outside function, the next step is find the derivative of the inner function, the 2x plus 1, and multiply the results from steps 4 and 5. The inner function and then the outer function, you need to multiply it, and you will get this value. Okay, simplify the chain rule derivative. So when once we simplify this one, we get this one. This is the value. This is the derivative for your dy by dx, dou y by dou x. Okay, so it is not a straightforward one, right? So you need to take the derivative of the outside function and then you need to multiply them. It's very simple. That's all. This is how it works. And what we are going to do is now we are going to use the chain rule, all the things to derive this one, to find out the derivative for this one. And we will see we're going to use the loss function gradient descent. With the gradient descent only will be keep updating once you find out the gradient. And what we do is we take the product of the gradient with the learning rate and then we subtract that from your current weight in order to get the new weight. Similarly, we do it for each and every the in the network, right? So each and every line, whatever the weights are there, we do it the same thing. So now what we will do is I just copy paste the same thing into the next slide. Where did I do that? Just yeah, this is the one for reference purpose. I just kept it here. So in this case, what we will do is we will calculate the net H1. So this is net H1 and out H1. Okay, here net O1, out O1, net O2. I have used some naming convention here so that while we do the derivation, we are not supposed to have any confusion. So here, what is the value for your net H1? Forward propagation. In the case of forward propagation, what is net H1? Net H1 is equivalent to W1 into your input 1 into your I1 plus W2 into I2 and B1 into 1. Here, look at the B bias is here because space is, I just put it here. B1 into 1. And if you simply plug in the value, you will get 0.15 into here I say 0.05 plus W2 is your 0.2 0.2 into 0.1 plus B1 is 1 into 0.35. Okay, and this one gives me 0.3775. Okay, and this one 0.3775. I'm not going to write it for everything because this one will get cluttered here. Okay, and then the next step is we need to use the activation function. This is the value of your net H1, which is nothing but Z net H1. And now we need to apply activation function on this Z value Z. When you obtain when you apply the activation function, what will happen? 1 divided by e to the power negative 0.3775. And this is the one 0.59 something will come. Okay, 593 something like that. Okay, this is what your out H1 value 0.593. This is what your out H1 value. So basically the sigmoid function, in this case, the sigmoid function is used. The sigmoid function squashes the value between 0 and 1, right? So this in this case, we are getting 0.593. And similarly, if you do the same thing for H2, you will get some value, right? So you need to multiply this one by this one plus this one by this one and bias into 1 into 3.5. You will get some value and you will get some other value here. So we're not going to write everything here, okay? It will take more time and it will be cluttered. Okay, we do the same thing for this net O1 and out O1. So what is the net O1 here? Net O1. We will just take, only this one, W5, this value into this one, out H1. Plus the W6 into the out H2. Okay. Yeah, out W6 into net 201. Yeah, for this one, it can't, it receives the input from these two things. Okay. W6 into the out S2 plus this is B2 into 1 because this bias is for your output layer. So B2 into 1. So what value we are getting it here? We are getting something like W5 is my 0.40 into my out H1 is 0.593 I mentioned, plus my W6 is 0.45 in this case, into out H2. Out H2 is let's say some value, okay, 0.5968 something like 5968 plus 0.6 into 1. So if you solve this, you will get something like netto one, right? So netto one, you will get something like 1.105905, something like that. Okay, netto one. Okay, and you need to use the activation function. You need to apply the activation function on this value so that we will get something like 0.75. That is what I mentioned here, right? 0.75 536 something like that. Okay, and yeah, this is for my netwo one, and the auto one is this one. So netwo one gives me the z value. When you apply the activation function on this one, you will get this one 7513. Yeah, this is the value 13 something like that, 75136 from here to here, here to here, and here, right? So this is the one gives us the predicted value, predicted probability as 0.5. The auto one gives us the predicted point 0.751. Similarly, we need to compute it for out O2. Okay, and this one and this one, and sorry, this one and this one, right? You need to take the product of this weight with this value and product of this value with this one, and then that value, for that value you need to apply the activation function. You will get a value for your outage 2, and then that value into this one and this one. Okay, and you will get the z value if you take the sum of these two weight and this value, right? And if you apply the activation function, you will get some other predicted value. In this case, the predicted value was given as 0.7 7729, I think so. I don't remember it. So this is the value. So now we need to calculate the total error, right? So here the total error is an E01 plus E02. That is what your total error. So in this case, the total error is your E total. One by two into target minus your output whole square. Output whole square in this case. So here it is nothing but the addition of these two things, E01 plus E02. Okay, and what is the E01? What is the error we are getting it? E01 is nothing but 1 by 2 into the actual is 0.01 minus 0.75136 or something like that. This is the one gives us the error as 0.2748. Okay, and similarly E02 if I compute it, E02 is let's if you do the same thing, right? So 0. 0, 2, 3. This is the error we are getting it. Now the objective here is when you add these two error, right? E1 plus E2, you will get, when you add these two values together, we get some total error 0.298. Now what we have to do is, this is the error. So the idea here is this error needs to be reduced. This is a cost. This cost function needs to be reduced. And how it can be reduced? Using gradient descent algorithm. So what we do is using back propagation. We call it back propagation. And so with back propagation, what we do is we pass the error from the output layer to the previous predecessor layer, and from the predecessor layer to the other layer, by changing adjusting the weights. In simple term, by keep changing the values for the weights, we will check at for which values of the weights the error is going to get reduced. This one we'll be doing it with a gradient descent. Okay, with the gradient descent algorithm, we'll be doing it. See, the idea of this one is to update each of the weights in the network, like how we did it. I demonstrated you in the linear regression, gradient descent for the linear regression, right? So in that case, what we do, we obtain the gradient. Once you obtain the gradient, we take the product of gradient with your learning rate, and then you subtract the value from your current weight. Thereby, we keep updating the weights in the network iteratively until the error becomes very, very small. Okay. Now what we will do is, to start with this, I just keep this as it is for our reference. I just copy and paste it in the next one. So now we'll start start with the output layer for the back propagation. We'll start with the output layer. Now we wanted to know how much a change in W5 affects the total error. We go in the last layer, okay, and then what it is, gradually you move to this layer, okay, and the input layer. Okay, the first we'll start with this layer, and here we are very particular. We wanted to know how much a change in W5 will affect the total error. So what is the total error? So now we need to take the partial derivative with respect to, so we need to take the partial derivative on the total with respect to dou W5. Dou E total divided by dou W5. We need to take the partial derivative on the cost function. You remember the same thing we did it there in linear regression, right? So with respect to W5. Okay, in this case, we are going to use the chain rule. Okay, we are going to use the chain rule. This is where the chain rule comes into picture. So in this case, the partial derivative of E total with respect to die, right? So we can also say this one, the gradient with respect to W5. By applying the chain rule, what we do, see in this case, I just tell you one simple thing. So this is your total, right? This total is, how you got this total? Because of applying the activation function. This total is depending on the auto one, and the auto one is depending on the netto one, and the netto one is depending on W5. If I write it here of the derivative, so this, this function, right? Sorry, this derivative can be this is a composite derivative function, which means this can be written as, we can write this with the different intermediary functions. Okay, here what I do is the total is depending on auto one, dou E total divided by dou auto one, because the error is depending on the auto one. So this is nothing but, this is a composite function. What is a composite? It's a nested function. This can be written like this. Okay, and auto 1 is depending on net O1 into dou net O1 divided by, sorry, sorry, this auto 1, right? So this one is depending on auto 1. Here the auto 1, dou auto 1 is depending on dou net O1 into this net O1 depends on dou W5. See, dou net O1 divided by dou W5. Okay. So if you look at only this part, right, you will be able to understand. Now we need to look at the total here. Now let us work on each and every derivative here, right? So this composite function or derivative, this composite derivative can be written as like this. Okay, to know the how much change in W5 can affect the error. To know that, we have to use this composite function. This function, right? For this, we need to take the derivative like this, because we cannot directly take this one, because directly we cannot compute this one, right? We need to take the partial derivative with respect to this one, because this one is depending on this one and this one is depending on this one. And first we'll take a look at the E total. The E total we have already discussed, right? So the E total is nothing but E1 plus E2, the EO1 plus EO2. So this one off into 1 by 2 into target minus output squared plus 1 by 2 into target, I say O2, target O2 minus out O2. Simply plug in the value here. So in this case, I just take the partial derivative with respect to auto 1, dou E total, because as per the gradient descent, right, we need to take the partial derivative with cost with respect to the last letter. First we need to find out, right? So dou auto 1, in the dou auto 1, how much change happened. So here, if you take the partial with respect to auto 1, we don't have the auto 1 here, hence this part will become 0. This one will remain constant and this one will get dropped, because we don't have the auto 1 here, right? Because we are taking the partial derivative with respect to we are taking the partial and E total with respect to auto 1. We can see auto 1 only here. And in this case, you learned about the chain rule, right? So the power rule comes into picture. 2 will come here, 2 into 1 by 2, and your target minus out O1, this 2 minus 1. We have taken the partial derivative. So we have taken the derivative on the outside function. Now we need to take the partial derivative on the inside function. So in this case, auto 1, what is the coefficient for auto 1? Into 1, right? So auto 1 is nothing but into 1. So which is nothing but minus 1. For the negative auto 1, the coefficient value is 1. Hence, when you take the derivative for this inside function, this one will go away and you are left with minus 1 here. Okay, so here this one will get cancelled, and here the target out to 1, this is out to 1, target O1. Okay, here what is the target value? Target value is 0.01, already we have seen it, and here the out 1 is 0.75136. If you subtract this, you will get some value here. 0. How much you will get? 74 something, right? Something. If 0.1 minus this one, will get 0.74136. This is the, likewise, we need to find out the value for each and every derivative here. Okay, so dou E total divided by dou out to 1. Okay, and then what is the next step? The next step is out to 1. What is out to 1? Up to this we are done, one step, and for this we are done, the 1, right? The 1 is over, and now we need to take we need to find out the value for the 2. And for the 2 out to 1, what is the out to 1? So here out to 1 is 1 by 1 plus activation function, right? Out to 1, 1 by 1 plus e to the power minus net over 1. The net over 1, whatever the z, right? The z, we take the activation function. So here, the out over 1 divided by, this is the 1. Then this is, what is this? This is what sigmoid function, right? Sigmoid function. When you take the partial derivative with your sigmoid function, what is the partial derivative? So 0 out over 1 divided by dou net over 1. So dou net over 1. When you take the partial derivative on the sigmoid function, it will be something like sigma into 1 minus sigma dash into 1 minus sigma. So in this case, the out over 1. In this case, it is going to be your sigma is, see, this is nothing but this one, right? This one represents this one. And I call this a sigmoid here, out to 1 into 1 minus out to 1. Out to 1 into 1 minus out to 1. Here, what is the out to 1 here? The output of this one, right? Out to 1 is your 0.7536. Into 1 minus the same value, 0.75136, something like that. When you solve this, you will get something like 0.186, something like that. Okay, you get some value. So next one is this one, the dou net O1 dou W5. So this is your dou out O1 by dou net O1. We are done with this. Dou out O1 divided by dou net O1. We are done with this. Second part is over. Okay. The next one is the third part. So net O1. What is net O1? This net O1 is depending on what? The W5 into out H1 plus the W6 into, see, this one is, for this, the inputs are coming from here and here. For this, the inputs are coming from here to here. So red color only, that's why I have given different colors here. So net O1 is nothing but W5 into your out H1 plus W6 into out H2. Out H2 plus the bias unit B2 into 1. If you plug in the value, you will get the value for this and dou net O1. For example, dou net O1 divided by dou W5 is equivalent to, and here if you take the partial derivative, what will happen here? W5, 1, okay, so here the W5 is going to be 1 here. When you take the partial derivative, this W5 is going to, the coefficient of W5 is 1, right? And into out H1. Out H1 into W5 to the power 1 minus 1. Chain rule. And the chain rule, the power rule also comes into picture. So here the W5, right? So to the power 1 is that one will come here, and out H1. Actually, sorry, the W5 to the power 1 is the 1 will come here. W5 to the power 1 minus 1, and then out H1. And then the next one is this one, right? So this part and this part, if you see here, we don't have W5 here, W6, and here the B2 bias 2 into 1. So this one will become constant, and these two terms will get dropped because we are taking the partial derivative with respect to W5. So hence, it will end here. So this one, what you get here finally. So here, W5 to the power 1 minus 1, 0. Anything to the power 0 is 1. So 1 into 1 is 1 into out H1, which is nothing but out H1. Out H1, we already computed, right? So out H1, how much we computed? The previous slide, this is what, 0.593. Already we computed it as part of your forward pass. I've gone somewhere else. The previous one, right? 0.593. In between, so many things are there. Okay. There's something about 0.593. So we computed the values for all these three things. And for this, the output is this one. And for the second part, this is the one we are getting it. And for this derivative, we got this value. So now if you put all these three things, this is 1, this is 2, and this is 3. When you plug in these values here, so dou E total, so dou W5 divided by, sorry, here dou W5 is equivalent to 0.7413 and 0.7413 into 0.186 into 0.593 is equivalent to, you will get some value. Okay, so this is 0.082, something like that. Okay. Then what is the next step? Next step is we need to update the weights. In this case, the weight is W5. W5 is equivalent to W5 minus eta into the dou E total by dou W5. You remember this is the cost. What is the cost function in our case? For this thing, dou E total by dou W5. Dou E total divided by dou W5. For this, we got this value, right? All these three things put together, I say this is A. We got the value for A as 0.082. So here, when you update this, this is the first iteration. What will happen is already the previous one is 0.40. 0.40 is the weight minus the eta is something like your learning rate. In this case, I say the learning rate is 0.5. You take a small value of your thing and 0.082. 0.082. Okay. So here, if you do the math here, you will get something like 0.35, something like that. Now we got the new weight, 0.35. So likewise, you need to take the partial derivative for all these things. The next step is we need to take the partial derivative for your hidden layer in order to get the in order to get the you know to yeah, you need to take the partial for your hidden layer. The same thing you need to do it here. Okay, so in this case, dou E total divided by dou W1. Okay, in that case, what will happen is we need to take the see in this case in this case the error, right? So the dou E total is depending on dou out H1 into dou out H1 is depending on your dou net H1, and your dou net H1 depends on your W1. Okay, you need to take the partial derivative. Right, so what will happen is when you do the partial derivative similarly for each and every weight, you will get new weight, right? So sorry, you will get the, when you take the partial derivative, you will get to know the gradient. Once you get the gradient, you can update the weight. In the first iteration, you are going to update the weights like this, and then you need to keep iterated as long as for these weights, what is the error? With the adjusted weight in each iteration, the weights will be, you will get a new weights, updated weights. With these new weights, what is the error? By keep iterating it, we're going to check, for which values of the weights the error is getting reduced. Right? That is when we conclude that the algorithm has been converged. Okay, or in other words, we can say at which point in time we don't see any more improvement in terms of reducing the error. Okay, that is how we decide, when to terminate this loop. So based on the number of iterations, whatever you specified, it'll it'll get terminated. Either you can use the iterations like I discussed as part of the gradient boosting for classification and regression, right? So the it will get iterated as long as the condition whatever you specified, all the values iterations, the number of iterations whatever you specified it, or as long as once the error gets super minimum, it will get end, right? So that is how we need to, or based on the conditions whatever we specify. What the conditions? The iterations only. We need to keep playing around with the iterations for 10,000 iterations. What's initially will get very less error for one iteration. One iteration itself we cannot decide it is really doing good job, right? So with multiple iterations, only we will get to know how much reduction error we can see it. So this is how it works, the back propagation algorithm. Okay, got it? This is very simple one. I just simplified this one. See, this total is depending on auto one because we are getting the predicted value from auto one only. Because in the auto one here, the activation function is applied on this one. Once the activation function applied on this one, it will give us the value. That value is going to be, in this case, it's a 0.753. But again, and the error is depending on this one. Now we need to compute the error. Error is depending on this one and this one, depending on the value emitted by this one, and then this one is depending on this one and this one. In order to find out the error with respect to W5, you need to go from here to here. This is how you can find out. Okay, so in the intro, they'll ask you the backward propagation, right? So how the back propagation works, they'll ask you, but we don't have to do anything for this. It is very simple. I just show you in the Jupyter notebook.